secant line intersects the circle twice. So I have a couple secant lines drawn there. Okay. Notice they create the red arc labeled x degrees, and they create the blue arc labeled y degrees. Those secant lines intersect inside the circle, and they intersect the circle, creating this arc here. Oh, shucks. Sorry. Here we go. They intersect this circle out here, creating this arc y, and over here, creating this arc x degrees. Okay? And so, the measure of that angle 1, do you agree that angle 1 and this angle here are the same? Okay, good. I'm glad you agree with me that they are. Can anybody tell me why they are?
Vertical angles.
What are they?
Vertical angles.
Vertical angles. It's been a while since we've used that word. But vertical angles are just these opposite angles that are formed when two lines intersect. The real definition is a lot more confusing than that, but that's what it means. And so those two angles are the same measure. And so the measure of one of those, I'll just erase my 1. And we'll talk about angle 1 then, this one over here. The measure of angle 1 is going to be half of the sum of the blue arc y and the red arc x. Half of the sum. So if I add those two arcs get together and divide it by 2, I'll get the measure of that angle. Okay. Unfortunately, secants don't always intersect inside the circle. Anybody not done with the picture? They don't always intersect inside the circle. Oops, sorry. Sometimes they intersect outside the circle. And when they do, the rule is still the same. Yes?
Yes, please.
What do you need?
The theorem.
My notes got changed a little bit, and so we're going to clean this up. I put this line here because this formula only goes with this picture. If they intersect inside the circle, then the measure of the angle is equal to half the sum of the angles. Okay? These other 3 pictures, which you'll want to copy down, did you get them all copied? Gosh darn it.
We didn't get the last
Last
one.
one.
Okay, let me move up a little bit.
Is that a dotted line?
No, it's just on an angle. The last picture, this is a minus. It's the sum. It's the half of the difference. Let's see if I can.
What's x minus y?
Oh, shucks, I wrote all over this, so I won't be able to.
But she said that.
Anyway, this is not a plus, it's a minus. Okay? So just to be totally sure you're clear, Theorem 1 only goes with this picture right here. Okay? Where the secant lines intersect inside the circle. This picture where the secants intersect outside the circle. This picture where a secant and a tangent intersects outside the circle. And this picture where two tangents intersect outside the circle. Have this rule that says the measure of the angle created by the secant or the 2 lines right here, this angle is equal to half of the difference of the big arc minus the little arc. Okay? And I'd already written on this, so I'll just, when I'm done, I'll get out of it, not save it, and I'll get back in and clean that up, so I don't have that problem again in the future. Okay, any questions on this page? All right, moving on then. Now we're going to talk about the segments created inside. Okay, the segments created inside are actually proportional. I'll pause this so you can copy this down. This dot here is actually the center of the circle, and it's only there to imply or to make sure you understand the intersection doesn't have to occur at the center, even though this is getting a little bit close. It doesn't have to occur at the center, but this segment here times this segment here is going to equal this segment times this segment. That means that those segments are proportional to each other because of the circle and the intersection inside. Okay, so we have two secants meeting inside the circle. Okay? On this picture, we have two secants meeting outside the circle. I'll pause it. Sorry, we found another error. This y shouldn't be there. And so it should be w times the sum x plus w equals y times the sum of y plus z. Let's go back up. I want to look at this one more time. You notice that this point right here is where the secants intersect, right? And so D represents the distance from the intersection to the circle. B represents the distance from the intersection to the circle. C represents the distance from the intersection to the circle. And A represents the distance from this intersection to the circle. And so each of those segments represent the distance from the intersection to the circle. If we move down to this picture, it's the same rule. Y is the distance from the intersection to the circle. Z plus Y represents the distance from the intersection to the circle, right? W represents the distance from the intersection to the circle, and x plus w represents the distance from the intersection to the circle. And so it's the same rule as this one, it's just that part of our distances overlap because the intersection is outside the circle. Okay? And so that's why this can't be a y here. It's got to be w, which is this distance right here from the intersection to that first part of the circle there. Okay? And then w plus x is this total distance here. And the same on the other side with y plus z and y. All right? And then the last picture is a tangent. It's a tangent and a secant. And because we have to have times, two segments times themselves, or the product of two segments, with the tangent we don't have two segments, we just have this one. And so to make it right, t squared is going to equal y times y plus z. And this distance here, y plus z, is the distance to the far side of the circle from the intersection. Today then, Wednesday the 18th, we're going to work on 11.4, 1 through 25 all. You'll notice Chapter 11, Quiz 1 is Friday. I don't think, I mean, I look at this, I know I obviously didn't. On Monday, 11.3, I think checkpoint quiz was with that lesson. So you need to go back and do that if you haven't done that before Friday to help you be ready for that quiz. Keep that in your notes. I'll add it to here, so, and I'll put the second one up, which was probably with 11.6. No, probably 11.5. Okay?